Yeah, let's welcome the next speaker.
Okay, hello everyone. I'm Seunghoon from Seoul National University. And today I'll be presenting our work on towards physically reliable molecular representation learning, which focuses on creating a more reliable potential model using limited data. So let's start with some background. Our primary task is the molecular energy prediction task, which estimates the total energy of a given molecule. So this is important because we can estimate the physical and chemical properties of a molecule. And based by these informations, we could even predict the chemical reaction on more complex systems. Traditionally, this task was done by using a very precise quantum mechanical calculation mechanism called the density functional theory, or the DFT calculation. However, due to its computational complexity, extending both spatial and temporal scales presents significant challenges. So recent studies have proposed replacing this traditional approach with deep neural networks or neural net potential models. Basically, these models are composed with GNNs or transformers or hybrid of those. Anyway, we expect the models to act as a surrogate function of the DFT, properly learning the underlying physics of the given system. So finally, our ultimate goal is to apply these models to predict the properties of a double molecules during material screening task. So the existing models are very accurate in estimating the energy. Here's one example. This table shows the errors in the total energy prediction task on the QM9 dataset, which comprises only stable molecules. We can notice that some errors are less than a quarter of the thermal fluctuations, which are about nearly 25 millielectron volts. So this is accurate, but our main question here is, does this small energy error mean a physically reliable model? Or do these models properly learn the underlying physical properties? Well, our answer was no. The performance of a model cannot and should not be determined by a singular metric of error in energy estimation. Then is there any way to, any method to examine the reliability? So one way to do is to testing their ability to optimize with structure optimization task. Okay, this is some background. The stable molecule is basically in its local minima of the potential energy surface. So when we perturb the position of atoms, the energy will increase. And if the perturbation is small enough, the molecule will naturally recover its stable state structure. So we began by optimizing molecules from QM9 dataset with our baseline models. But unfortunately, previous models fails to restore the stable structure for most molecules. This indicates that these models are overly optimized for only energy estimation. And this may not provide a comprehensive understanding of the system's physical properties. So why does this happen? The core issue to this problem is that we have such a limited amount of data points, but the chemical space the model has to search is vast. For example, we have a ground truth potential energy surface for a certain composition. Here, the structures and energies are given, and the model tries to estimate, to predict the ground truth energy PES. However, due to the enormous amount of degree of freedom, the model is likely to estimate a meaningless energy surface. So now let's think about the case when we're using additional information. For example, let's consider a case where the gradient of the energy surface is given in every data point. By doing so, we could dramatically reduce the chemical space that the model has to explore. So eventually it will yield a much more accurate potential energy surface. Therefore, optimally utilizing the physical constraints is essential when training a potential model. So from here in this section, I'm going to elaborate on our constraints and training methods. First, we began by applying a physics model constraint in energy calculation. When estimating the energy, we considered the self-energy of a single atom and the bond energy between pair of atoms. And we allowed 3 fundamental rules for the bond energy. Let's look at an example. First, when the atoms are too close, the energy rises rapidly and must result a repulsive force. And second, in the limit of infinite distance, the energy and force become 0. And lastly, at any equilibrium infinite distance, the energy reaches its global minimum while the force becomes 0. This is what we call a stable state. So one of the most simple equations that satisfies such conditions is the Lerner-Jones potential, which primarily models the potential energy due to the van der Waals force. Further, to model the long-range interactions, we also introduced the electrostatic potential. So our model estimates the parameters represented by beta in this equation. And betas functionally depend on the species of atoms, species of pair of atoms, and their distances. So by this, we could dramatically reduce the chemical space that our model has to search. And next, we incorporated two important constraints inspired by physics. This is particularly applicable when we are dealing with a stable structure. The one is the inequality bound condition. As mentioned earlier, when you slightly perturb a stable molecule, the energy will increase. So in our model, we input both a stable structure and a slightly perturbed counterpart. So if the model predicts a lower energy for the perturbed structure than compared to the true energy of the stable one, we penalize our model. The second constraint is a zero force condition. This is based on our simple understanding that in a stable structure, the mean of the net force should be 0. And finally, we integrated a simple self-supervised learning framework named as the mass atomic modeling. So here's how it works. We take the atomic embeddings from a molecule, and then we zero out 30% of them. Then our model is forced to fill the blanks, predicting the original atomic species which are hidden. So to correctly recover this, the model has to focus on the overall structure of the molecule. By this, we expect our model to learn the fundamental bonding principles. So in this section, I'll explain about our experiment setups and the major results. In our experiment, we adopt 2 noble matrices to measure the generalizability of our model. When structure optimization is applied, we can measure the structural distortion and the energy difference between the resulting molecule and the ground truth molecule. Here, the structural distortion is noted as delta P, and the energy difference is denoted as delta E. We can use them to see whether the model learns a meaningful energy surface. In an ideal case, the model perfectly learns the ground truth energy surface, and the Bose matrix will become 0. But in a problematic case, the model fails to learn a reliable energy surface, and the resulting molecule will have huge discrepancies to the ground truth molecule, and the Bose matrix will become larger. So here we benchmarked our model in QM9 and OC20 dataset. QM9 dataset consists of only stable molecules, while the OC20 consists of both stable structures and unstable structures. So here we evaluated our model with three metrics. First is the energy MAE, which measures the estimation error of the total energy. And second, force MAE quantifies the estimation error of the force. And this should be 0 for the stable molecules in the QM9 dataset. Lastly, we use our new metric, the delta P, the position distortion. In the QM9 dataset, our model demonstrated an energy estimation error that was comparable to the current baseline models. But our two differentiation emerged when we compare our model with force MAE and delta P. Here, our model outperformed the baseline model substantially, implying a much more robust learning of the inner surface. And this is also aligned with our observation that the baseline models fails to optimize even to a stable structure. However, when we trained our model with only energy loss, the force MAE and delta P results became similar to the baseline models. This demonstrates the vital role of incorporating additional physical constraints into the model. And moreover, when we trained our model with only energy loss, when we extend our experiment to the OC20 dataset, our model exhibited superior performance compared to the baseline models in both energy MAE and delta P. Next, for the QM9 dataset, we conducted a comprehensive set of optimization experiments. In this phase of our investigation, we utilized our two new metrics, the energy difference and the structural deviation between the ground truths and the optimized molecule. As you can see in the table of the right side, our model reduces both matrix for more than an order of magnitude, achieving more than a tenfold decrease compared to the existing baselines. We also visually inspected results of structural optimization, which are illustrated in the figure to the left. So you can see our model recovers the stable structure, while other models catastrophically fails. Further, to check the robustness of our model, we conducted extensive experiments on more complex molecules. So as you can see, other models fails to restore the stable structure, but our model succeeds in recovering the original structure even for more complex systems. We also conducted experiments to check whether the model learns the overall molecular structure when adding the masked atomic modeling. Here we masked the atom of interest and drag the atom along the z-axis. And we could see that the model assigns a higher score to the ground truth species. Here, the heat maps on the right side represents the predicted score of the masked atoms by our model. Here we observe some interesting details. Then when the drag distance is large, the model assigns a smaller score to the ground truth species, which means that if the molecule becomes unstable, the uncertainty becomes larger. So overall, this result suggests that our model could also comprehend the structure of the molecule. So the next question was, can our model generalize beyond the stable structures? To assess the generalization capabilities of our model, we devised two critical tasks. The first thing is the total energy prediction along the reaction pathways, and the second one is the reaction barrier estimation. For the first task, we incorporated a pre-training step on the QM9 dataset, followed by a fine-tuning step in the transition 1x dataset. Here, the transition 1x dataset consists of nearly unstable structures. Remarkably, our model demonstrated significant accuracy predicting the total energy for even those unstable structures. And we also conduct a test called the reaction barrier estimation. When a chemical reaction occurs, the reactant, which is the molecules on the right side, must overcome a certain energy barrier. This is called the reaction barrier. So accurately predicting the barrier height is closely related to the generalizability towards reactions. The result is like this. Our model exhibited a notably smaller errors compared to the thermal fluctuation. This indicates that our model possesses the capacity to generalize beyond stable molecules and accurately infer the energy barriers during chemical reactions. Further, we test our model using a more challenging task. We split a stable structure to two functional groups and make our model to optimize the whole system for 500 steps to see whether our model recovers the stable structure, the original structure or not. Using the test data set in QM9, some systems were actually recoverable, while other models catastrophically failed. From A to B, we can see our model recovering the original structure. One remarkable thing here is that the recovery was only done with including the inequality bound condition. As shown in the figures to the right side, our model fails to recover the original structure. Therefore, we concluded that this plays a key role in generalizability beyond the stable states. So in summary, we can conclude our research into two main parts. First, we facilitate a more physically reliable model under limited data by incorporating physical constraints and self-supervised learning methods. And here we can point out three details. The inequality bound condition was the crucial part for the most crucial part for the model to understand the physics near the ground states. Next, the zero force condition was very fruitful for optimized structure-only datasets. Finally, the mass atomic modeling helps the model to understand the basic bonding natures. So with this embedding in the training step, our model was able to generalize beyond the stable structures, including the reaction barrier prediction and the molecular assembly task. So this is the end of our presentation. I hope you enjoyed it. Thank you.
Let's welcome Chung for the discussion first.
Hi, I'm Chung Liu from UC Santa Barbara. It's my great honor to be a discussion of this nice oral presentation. So here are some very interesting takeaways. So the first, the problem. The problem is studies molecular representation learning, which is to predict the total energy of a certain molecule. And there are some key challenges. The first, that is limited label data. Due to the chemical reactions, we usually have the data of the stable states, and we have very limited data in unstable states. And also, the simulations are usually very expensive in terms of money and time. And finally, the key challenge is that the validation is very hard because we need a physically reasonable molecular. And lastly, the key techniques, including 4 parts. The first is the molecular attention block in the transformers, which is able to model the relationship between the different atoms. The second part is a physically parametric model, which is used to predict the energy. The third key part is masked atomistic modeling. And then the final part is combining the physical constraints such that we can have some physically valid molecular. And I do have 2 questions. So the first is, what are the applications of the molecular representation learning? And what are the current companies and the industry are currently using it?
Okay. For the first question, as I mentioned, this is widely used in material screening task. For example, displays like phones or computers, they are very essential to estimating the homoluminal gap of a given molecule. So for a specific example, Samsung uses such softwares or models to predict the noble molecules they suggested in the first extensive throughput screening step. So To summarize my explanation, that is widely used in the primary step of material screening.
Thanks. My second question would be a molecule usually have different elements atoms. For example, there are some relationship between carbon and oxygen and also the relationship between the carbon and the nitrogen. So are the different functions, not just RBF functions, needed to model different relationship between the atoms?
So the question is,
Do you
what
consider different functions to model the different relationship between different atoms, not just RBF function?
Yep. No, we just use the RBF functions to model the bondings between atoms, but the basis set of the RBFs are different by atoms. So, for example, if there are eight species of atoms, the 8 species of atoms will have a different basis set of its own. Yeah.
Okay, thanks.
Yeah, thank you. We can take one more question from the audience. Any question? Yes.
For the interesting talk. I just wanted to ask about some details of your algorithm. For instance, your database, as far as I know, only contains, and again, please correct me, only contains stable molecules. So did you do the energy calculations for the perturbed states, or did you only use them to in the model? So did you have the ground truth energies for the perturbed states that you introduced?
The answer is yes or no in both cases. In the transition 1x dataset, we have both the ground truth energy and the force for the unstable structures. But in other cases, when we perturb the molecules in the QM9 dataset, these don't have a ground truth energy.
Did you do the DFT calculations when you didn't have it?
Oh no, we do not do the DFT calculation steps.
Thank you.
Thank you.
Thank you.